Hello everyone, welcome back to the MOOCs course on Advanced Analytical Technique. Today we are going to start the second unit of this course, and the title of this unit is Molecular Luminescence Spectroscopy. This is the first lecture of the fourth week. Let us now begin the concept of molecular luminescence spectroscopy. The molecular luminescence spectroscopy, or in short ML spectroscopy, refers to the study of emission spectrum of excited molecules. So in one sense we can say that it is also a type of spectrum that is related to our atomic emission spectroscopy. But the difference is that in case of emission spectroscopy or the atomic emission spectroscopy, the sample emits light by absorbing of heat. But in this particular case, there is no heat source used. The substance emit light based on its cold body conditions, means the sample is not heated by any source, neither by flame or by a plasma or an electrical heating. Instead we use a light source to excite the sample, means the absorption is also taking place, and then the excited sample returns back from the excited state back to its ground state, releasing light radiations which are being captured by the detector. So an emission spectrum is generated. In one sense we can say that both the phenomena of absorbance as well as emission, in one sense we can say that both the phenomena of absorption as well as emission is taking place in case of molecular luminescence spectroscopy. And that is why I have covered the absorption and emission spectroscopy in unit 1, so that when you got an idea about the concept of absorption and emission spectroscopy, it would be very easy for you to understand the ML spectroscopy. So here we have, first of all, we have, for example, we have an atom present in a sample. This atom is excited by a light source. We generally use UV light in this particular case. The absorbance of light causes excitation of electrons from the ground level E0 to the excited level, and when these electrons come back, they emit light, which creates an emission spectrum. So fluorescence spectroscopy is basically a type of emission spectroscopy, but it involves the phenomena of absorption as well as emission both. So the sample molecule absorb a light photon causing excitation. So this excitation, it is due to absorption of light photons. Sometimes this excitation can also occur by a chemical reaction if light absorption is not taking place. In some cases we have excitation of electrons due to chemical reaction only, based on its chemical energy. In that case also we see some light radiations coming out from a sample. That particular type of emission, that particular type of emission is called as chemiluminescence, that we'll discuss later. So far but till now it is also a type of molecular luminescence, which is created by the action of chemical reaction, by the energy provided by a chemical reaction. So in broader sense we can say that ML spectroscopy, so in broader sense we can say that molecular luminescence refers to the emission of light from a sample either by absorption of light radiation or by a chemical reaction. This emission of light is called as luminescence, and since it is given by a molecule, because we are not atomizing a molecule into individual atoms like we do in case of atomic emission or atomic absorption spectroscopy, there we use the word atomic before absorption and emission, which says that our focus in that particular case is on the individual atoms or elements, I should say. Therefore we atomize the sample completely, dissociate it into individual atoms and then excite those atoms. While in this case we use the term molecular luminescence, it means that we are not going to atomize these molecules, we are not going to dissociate these molecules into individual elements. We directly take the sample and the molecules present in the sample are excited either by and the molecules present in the sample are excited by a light radiation, incident light radiation, which causes excitation of electron upon absorption, and when the electrons come back, light of longer wavelength is emitted, creating a fluorescence spectrum, which is a type of emission spectrum. This can also be observed by chemical energy from a chemical reaction. So this emission is called as luminescence. However, this luminescence is quite different from incandescent, which is the emission of light by heating. I hope you all have seen the incandescent bulb, the yellow color bulb which we use few years back, maybe a decade back where we have these types of bulbs, that gives yellow light. These bulbs are called as incandescent bulbs, where we have a filament made up of tungsten, and that filament is heated at very high temperature by passing current between the two electrodes, and at very high temperature it starts emitting light radiations. So that is called as incandescent, and that is called as incandescence. And incandescence means the emission of light by absorbing heat, while luminescence means emission of light by absorbing incident light radiation of lower wavelengths. So incandescence means light emission by absorbing heat. Light emission by absorbing heat. Light emission by absorbing heat. It's called as light emission by absorbing heat, while luminescence means light emission by absorbing light of lower wavelength and emitting light of longer wavelengths. So this is the difference. So this is the difference between incandescence and luminescence. Now these molecular luminescence phenomena are divided into three groups. First is called as the fluorescence, then we have phosphorescence and chemiluminescence. Fluorescence is defined as the emission of light of longer wavelength from an excited species after it absorbs light photons, while phosphorescence is also the emission of light of longer wavelength from an excited species after it absorbs a photon. Now then what is the difference between the two? The difference between these two phenomena of fluorescence and phosphorescence is that their existence. While fluorescence exists for a very short time, it is called as a short-lived phenomena, because it involves high energy singlet state. On the other hand, phosphorescence is a little bit long-lived phenomena. It exists for a comparatively longer period of time because it involves the low energy triplet state. Here we have a triplet state, while in this case we have a singlet state. So which means that fluorescence is the emission of light of longer wavelength upon absorption of light of shorter wavelength, and as soon as we stop the incident light, the emission of light from the fluorescing molecule is stopped. On the other hand, phosphorescence refers to the emission of light of longer wavelength upon absorption of light of shorter wavelength, but the phenomena of emission of light continues for a little bit longer period of time even after cutting off the incident light radiation that is being irradiating the sample. So this is the difference between these two. The concept is same, but the duration of the emission of light basically keep this process apart. Then we have a third photoluminescence phenomena called as the chemiluminescence, which refers to the emission of light from a molecule due to chemical reaction. Here we do not need an excitation source. No light source is needed for excitation, no light source is needed for exciting the molecule. A chemical energy is released by a chemical reaction that excites the molecule, resulting into the emission of light from that molecule. And this phenomena you might have observed from some insects as well, and even especially during night time you observe this phenomena near sea beaches, where aquatic organism show chemiluminescence and you can see light radiations from the water. History of these two phenomena. Although both history of these two phenomena, because both these phenomena are natural phenomena, they have been discovered long back, but their name was given a bit later. They both have a very rich and fascinating history. Even in the 15th century, in the year 1565, there was a scientist, Nicolas Monarch. He was a botanist as well as a physician. He was a botanist as well. In the past, people may have more than one skill. In the present time, we have one person specializing in one particular area who does not have any knowledge of some allied areas. But in the past, you might have heard about some physicist who got Nobel Prize in chemistry, some chemist who got Nobel Prize in biology. Many of the people of yesteryears I can name who were mathematicians as well as astronomers, and they have knowledge of chemistry as well. So at that time we have a person with more than one skills. So at that time we have person with who is expert of more than one area. So Nicolas Monarch was also a botanist as well as a physician, and he observed and reported that infusion of the extract from the wood of Lignum nephriticum into the patient vein, and when the veins are being seen in sunlight, they are exposed to sunlight, they show blue color. This was the first report of the phenomena of fluorescence. This Lignum nephriticum, this tree is also known as kidney tree. The extract of the wood of this tree, Lignum nephriticum, is used as a diuretic. Do you know what is diuretic? Diuretics are the medicines or the drugs that are used to increase the urination of a person. In case if the person is having some sort of infection or it is having high blood pressure, hypertension, then in order to reduce the salt level, in order to maintain the salt level as well as the hydration level, these diuretics are being given to the patient, which ultimately helps the patient to maintain the body fluids, the salt level, and in this way the patient can maintain its blood pressure. Especially in the past, these wood extract or other natural products are being given to the patient as a diuretics. So this was the first report of the phenomena of fluorescence, or I should say it is the first document of the examples of fluorescence. Then in the years 1603, means in the 16th century, there is an Italian scientist, Vincenzo Cascalerio. Then in the year 1603, means in the 16th century, there is an Italian scientist, Vincenzo Cascariolo. Vincenzo was working on Bologna stone, and when this stone was exposed to sunlight, he observed that the stone is emitting light radiation. Even after when the stone is placed inside, means it is not directly exposed, even after putting it inside, the stone continues to emit light radiations. So this was the first report of the phenomena of phosphorescence. While the reports of Nicolas Monarch was relating to the phenomena of fluorescence, where the extract of the wood of Lignum nephriticum into the veins through infusion shows blue color of the vein when they are exposed to sunlight. But in this case, Vincenzo Cascariolo, he showed that even he reported the phenomena of phosphorescence when Bologna stone was exposed to sunlight, it started emitting light radiation, and even after keeping it inside, the emission of light continues for a certain period of time. So these reports are considered as the first report of these phenomena of photoluminescence. Then in the year 1852, Sir George Gabriel Stokes, he was a British physicist, he gave the first explanation of the phenomena of fluorescence. He was working on some fluorite minerals, and there he observed that these minerals emit blue light when illuminated with ultraviolet radiation. So he took those minerals and he irradiated them with UV light, and then he observed that the molecule that these fluorite minerals emit blue light, means visible light. And based on the name of the mineral fluorite, he gave this phenomena, he gave the name to this, and based on the name of this mineral fluorite, he gave this phenomena the name fluorescence. And based on the name of this mineral fluorite, he gave this phenomena the name of fluorescence. So he was Sir George Gabriel Stokes who coined the term fluorescence based on the fluorescence properties of fluorite minerals. Clear? He also showed that the light radiation that is being absorbed by these fluorite minerals was of lower lambda and higher energy, while the light that is being emitted by these minerals was of longer lambda and lower energy. This is the light that is being absorbed, and that is why because this is UV light which is having, because this is UV light he irradiated the samples with, which is having high energy and lower wavelength as compared to the visible light that is being emitted. And later the difference between the wavelength of the light absorbed and the wavelength of the light emitted is called as the Stokes shift. If in case the wavelength of light absorbed and the wavelength of light emitted is exactly same, then the difference between the peaks then there will be no difference between these two peaks, and we can say that the Stokes shift is 0. But this is not the case with fluorescence, but this is not common in fluorescence. In case of fluorescence, the light which is being emitted by the sample is always of longer wavelength and lower energy than the light which is being absorbed. We will discuss these Stokes shift in the later parts of this lecture. So his pioneering work, the work of Sir George Gabriel Stokes. So Sir George Gabriel Stokes laid the foundation of the understanding of the photoluminescence phenomena. There people understood that fluorescence consists of excitation, or I should say absorption, as well as emission. Means both the phenomena, the absorption of light as well as emission of light, they are taking place sequentially, one by one. First absorption or excitation is taking place, then we are having emission of light. These two phenomena collectively form the phenomena of, these two phenomena collectively creates the phenomena of fluorescence. Now the phosphorescence was studied in detail in the 19th and early 20th century. Particularly after the development of quantum theory, the phenomena of phosphorescence was understood in detail. Scientists discovered later that the difference between these two phenomena, as I said, the only difference between those two phenomena is the period for which the light is being emitted. In case of fluorescence, the light is emitted for a very short period. Once we cut off the incident light radiation, in case of fluorescence, the light emission is immediately stopped, while in case of phosphorescence, even after cutting off the supply of incident radiation, the sample continues to emit light radiation for a certain period of time, and therefore The only difference is the time period for which the emission of light exists in these two samples, and scientists later discover that this difference is due to the electronic spin states of these two phenomena, which means that fluorescence involves some other spin state while phosphorescence involves some other spin state, which means that fluorescence involves one spin state while phosphorescence involves the other spin state, which I'll be showing you in the next slide. They further reported that in case of fluorescence, the transition of electrons involves a singlet to singlet transition, means the transition is possible. The transition involves from ground state, of course it is having from ground state to even, or sometimes it is from, or sometimes from ground state it is going to E2, but in these two cases we have singlet state, we have singlet spin state in the ground state as well as singlet spin state in the excited state, and when these electrons from singlet state come back, they emit light, and since singlet state is short-lived state, the light immediately disappears as soon as the incident light is stopped. If this is the instant light, the moment we stop this instant light, instantaneously there will be no light emission from the sample. But in case of phosphorescence, since the excitation involves a triplet state as well, how that triplet state is involved, that I am going to discuss in the next, that I'll tell you in the next slide. But phosphorescence involves a triplet state as well, and since triplet state means actually the transition starts from singlet to singlet, and then from singlet the electron goes to triplet state, and then finally it comes back. So singlet to triplet, and then finally it comes back to singlet. So therefore, and since, so from singlet to triplet, and then finally it comes back to singlet, and in this case you can see that triplet state is involved, which is long-lived state. Therefore in case of phosphorescence, the substance continues to emit light even after the incident light is cut off. This is the famous Jablonski diagram. This is the very basic form of Jablonski diagram. The advanced form showing detailed phenomena relating to the photoluminescence will be shown in the next lecture. But here this simple figure helps you to understand the phenomena of fluorescence as well as phosphorescence. This famous Jablonski diagram was given by Alexander Jablonski in the year 1933, and that is why this diagram has been given the name Jablonski on the name of the person who discovered this diagram. So in this figure you can see that we have a molecule in the ground state, and this molecule receives light radiation, means light photon h nu. Once these light radiation are being absorbed by the molecule, it causes excitation of its electron. The electrons are promoted from ground level to the excited level. Now there are two possibilities. In the ground state, the spin is paired, therefore it is singlet state, sometimes referred to as S0 because it is the ground state, so we put a 0, and the excited state is written as S1 because it is the excited state, but the electrons are still paired, because even in UV spectroscopy there is a selection rule which says that transition of electron always occurs with retention of spin. Very famous rule, very famous selection rule of ultraviolet and visible spectroscopy, or the other name is, or the alternative name is electronic spectroscopy, that transition of electrons always occur with the retention of spin, which means that since in ground state the spin is paired, the transition always occurs with the retention of spin, means even in the excited state the spin remains paired. So the transition is occurring from S0 to S1. Now From S1 directly the electron returns back emitting light radiation. This is called as fluorescence. But in some cases, at this stage, because singlet state is high energy state, so it is less stable. Why? Because in this state we have two electrons in the same orbital, and since electrons carry negative charge, so these two negative charge have some repulsion, causing this state to be little bit, causing this state to be less stable, and therefore they emit some light radiation, they emit some energy in the form of non-radiative energy, which means they lose energy, but not by emitting light but by emitting heat. So not radiative relaxation means the electrons release some of their light and changes their spin from singlet to triplet. Now they come to triplet, which is a little bit lower energy state, and that's why it is more stable here, because in this particular case we have electrons in different orbitals because spin is parallel, and therefore repulsion is lower, and repulsion is lower, therefore we have more stability. So electrons from high energy state reaches to low energy triplet state, from high energy singlet state by a non-radiative loss of heat, by a non-radiative loss of energy, which is in the form of heat, not in the form of light. So when they come from S1 to T1, and then from T1 they come back, so from S1 to T1 they are coming, and then from T1 they are coming back directly to the S0. This 3 means it is triplet state, 1 means it is singlet state. So we can say that, so I can show you that, so I can represent the phenomena of phosphorescence like this: S0, it is going to S1, from S1 it is going to T1, and from T1 it is coming back to S0. So this is your phosphorescence, while fluorescence is S0 to S1 and S1 to S0 coming back. And why these are called as singlet and triplet state? This is by calculating the multiplicity, which is I is equal to 2s plus 1, and this is spin. In case of paired we have plus half and minus half, making it 0. So if we put the value of s, we have 2 multiplied by 0 plus 1 giving 1, so it is singlet state, while in case of triplet state we have unpaired or parallel spin, so we have 2s plus 1 and s is equal to 1 by 2, again 1 by 2, both are having plus charge, so it comes out to be 1. If we put this value of 1, 2 into 1 plus 1, so if we put this value 2 into 1 plus 1 giving it 3, so that's why it is called as triplet state, while it is called as singlet state. Going to the next slide, the definitions of fluorescence and phosphorescence again. So the definition of fluorescence and phosphorescence: fluorescence is defined as the emission of light from a substance upon fluorescence is defined as the emission of light by a substance upon absorption of light of shorter wavelength, and this light is stopped, and this light emission is stopped as soon as we stop the incident light radiation. And the phenomena of fluorescence involves singlet state, while phosphorescence is defined as the emission of light by a substance upon absorption of light of shorter wavelength, and the emission of light is continued even after the light radiation, the incident light radiation is stopped, and this phosphorescence phenomena involves the triplet state. The mechanism, as I just mentioned, for example, if we have a molecule where electrons are present in the ground state, means singlet state, when it absorbs light radiation, Ex shows it is the excitation, means the incident light radiation. The electrons may be excited to the first excited level or even to the second excited level, and when these electrons come back from the excited level S1 or even from S2 directly to the S0, the light emitted is called as the fluorescence light. On the other hand, if from S0, on the other hand, if from S1 the substance goes to T1 by emission of non-radiative energy, means, and then from T1 they are coming to S0 by releasing light radiation, then it is called as phosphorescence. In this slide, let us discuss about the Pauli's exclusion principle, which you all must be aware of. According to the Pauli's exclusion principle, no two electrons in an orbital can have this. According to Pauli's exclusion principle, no two electrons can have the same value for all the four quantum numbers, which means that for two electrons that are present in the same orbital, since for these electrons the value of principal, azimuthal as well as magnetic quantum number is same, therefore they have a different value of spin quantum number. One is having a plus half spin, which is clockwise, while the other is having minus half anti-clockwise. So these two electrons, they can only remain in an orbital if their spin is paired. If their spin is not paired, they cannot remain in single orbital. They have to be in two different orbitals to have their spin parallel. So the same is being written here. Orbitals can contain a maximum of two electrons, and these two electrons must have opposing spin. They cannot have same spin. If they have same spin, they must be present in different orbitals. But if they are present in same orbital, their spin must be paired. Here you can see, in this particular case, we have, here you can see, in this particular case we have the electrons paired. One is having the one is showing the direction upward while the other is downward, so it is clockwise, it is anti-clockwise. For this one we have plus half value, for this we are having minus half. Here also it is paired, but if they are unpaired, then they must be in different orbitals. They cannot remain in the same orbital if they are having same spin. So it cannot exist like that. If the two electrons have parallel spin, they have to be in different orbitals. It is not possible that two orbitals that are present in the same orbital, it is not possible that two electrons that are present in the same orbital, they have parallel spin. It is not possible. If this has to be the case, the electrons should be in different orbitals. Now, singlet and triplet state, as I said, ground state always, in ground state electrons are always paired, means in ground state we have two electrons in an orbital in which one is having clockwise or plus half value of spin while the other is anti-clockwise spin. Now in singlet state also, now in singlet excited state also we have, now in singlet excited state also we have spin of the two electrons paired, which means that they have same spin as they have in case of the ground state. Again it is paired spin, so it is a singlet state. Now triplet state refers to the state in which the two electrons are present in different orbitals, and that is why only they have parallel spin, which means that they both have a clockwise spin. They both have the value of spin quantum number as plus half, while in singlet it is always 0, because one is having plus half, other is having minus half. It is 0 in the singlet state, in the singlet excited state, while in case of ground state also one is having plus half, other is having minus half, to give 0. But singlet states are less stable because they are more energy state. Why? Since electrons having same charge and they are present in the same orbital, so they are very close to each other, causing repulsion, making the state less stable. On the other hand, in the triplet state, electrons are having parallel spin, which means that they are placed in the different orbitals, so they are far away, and therefore they have no repulsion, or I can say very little repulsion, and that's why this state is more stable. This is the theory of fluorescence and phosphorescence. Here the time lapse of the time required, for each phenomena is presented. The absorption of light of the molecule is a very quick phenomena which happens in 10 to the power minus 14 to 10 raised to the power minus 15 seconds, means even less than a picosecond, this absorption of the light taking place, causing excitation. And when the electrons are excited to the next level, now they can come back. They either come back directly from the excited singlet to the excited, they can come directly from excited singlet to the ground singlet. In that case, it's called as fluorescence, for which the time lapse is 10 to the power 9 to 10 raised to the power minus 7 seconds, or I can say from 1 to 100 nanoseconds, while the absorption or excitation, it is even lesser than 1 picosecond. Very fast phenomena. On the other hand, phosphorescence, the phenomena, as it is a long-lived phenomena, the light is being emitted even for a longer period of time. The time ranges from 10 raised to the power minus 3 to 10 raised to the power plus 2 seconds. Means for phosphorescence, we can have, means for phosphorescence, the time lapse is from 1 millisecond to 100 seconds. So we can witness phosphorescence even up to 100 seconds after the incident light is removed. And then, as I said, in case of when we have from singlet to triplet transition by a non-radiative energy loss in the form of heat, for this the time lapse is 10 to the power minus 8 to 10 raised to the power 9, means 1 to 10 nanoseconds is required, means 1 to 10 nanoseconds are required for non-radiative heat transfer. So based on this theory, we can say that the quickest phenomena is the excitation of electron by absorption of light. Then in terms of time lapse, in terms of the existence, we have fluorescence, which exists from 1 to 100 nanoseconds, and the non-radiative heat and the non-radiative energy loss in the form of heat, which also exists for a very short period of 1 to 10 nanosecond, but the phenomena of phosphorescence can be lasted from 1 millisecond up to 100 seconds. So this is the time duration of these phenomena. Both these phenomena of fluorescence as well as phosphorescence can be used for qualitative and quantitative analysis, just like we can use atomic absorption and atomic emission spectroscopy for both qualitative and quantitative analysis. In this slide, fluorescence is compared with UV visible spectroscopy. Here you can see that with UV spectroscopy we can go up to very low detection limit. This UV visible spectroscopy helps us to identify moles even if they are in very little in number. 10 raised to the power minus 13 to 10 raised to the power minus 16 moles are present. Although moles contain quite large number of molecules, it is equal to Avogadro's number 6.023 into 10 raised to the power 23 molecules are present in a single mole. So UV visible can be used for the detection of moles from 10 raised to the power minus 13 to 10 raised to the power minus 16, while fluorescence can be, with fluorescence we can go either lower values from 10 raised to the power minus 15 to 10 raised to the power minus 17 moles we can go up to, means even it is 10 times more sensitive as compared to our UV visible technique. On the other hand, in terms of concentration, here we have in terms of mole, in terms of concentration, we can go from 10 raised to the power minus 5 to minus 8, means from 10 micromolar we can go up to 10 nanomolar concentration, while in case of fluorescence, again it is more sensitive, the detection limit is even lower. We can have the detection of sample from 100 nanomolar to 1 nanomolar. We can, here also we can go up to 10 times higher. So in this case also we can have detection limit even 10 times better than UV visible spectroscopy. Therefore, although UV visible is a universal technique which can be applied to nearly all molecules because all the molecule absorb light radiation, fluorescence is quite sensitive. It can not be applied to all the molecules. It can only be limited to the molecule that fluoresce, or if the molecule do not fluoresce, we can make them fluoresce by artificial fluorescence to make them fluoresce. So fluorescence is a sensitive phenomena. It cannot be applied to all molecule. It can only be applied to the molecule that show fluorescence, or if they are not showing fluorescence, we make them show fluorescence by adding some fluorescence dye, which is known as artificial fluorescence phenomena, that we'll discuss later. So UV visible quite universal, while our fluorescence it quite is, while our fluorescence is quite sensitive. This is being shown here. A sample is being irradiated with light and the transmitted light is passing through the sample, but we are concerned with the light that is being emitted by the sample upon absorption of light. While in this case, in case of UV visible, we measure the incident light and the transmitted light and notice the difference, because this difference of the intensity of the incident and transmitted light basically gives us an idea about the light intensity that is being absorbed. But in case of fluorescence, we do not focus on transmitted light radiation. We have nothing to do with it. We let it pass through the sample. We focus on the light that is being emitted when the electrons returns back. Let's move to the next slide. This is the phenomenon. So these figures shows the phenomena of fluorescence and phosphorescence. In fluorescence, we have these a molecule showing fluorescence, a substance showing fluorescence looks like this, while in case of phosphorescence, we have it completely dark and very little portion is being eliminated, while in case of phosphorescence, it is dark and very little portion is being illuminated. It exists for 0 seconds even when the light is removed, while it exists for certain period of time. Even in some cases, it can go up to hundreds of seconds, means we can go up to 1 minute in case of phosphorescence. So this is the difference between the appearance of these two phenomena. With this, I am going to end this lecture, and in the next lecture we will discuss about the Jablonski diagram in detail and the factors affecting the phenomena of fluorescence and phosphorescence. Till then, thank you very much.